We continue with the discussion of flow past a rigid sphere for viscous fluids, and we had obtained the values of the velocity components ur and u theta. The two solutions which were indicated by equations 69 and 70, then obviously they are derived for the case when the sphere is at rest and the velocity of the fluid at infinity is u. Now, to obtain the solution when the fluid is at rest at infinity and the sphere is moving with velocity minus u, so we subtract u cos theta and minus u theta from these equations, and we obtain from the equation above, and we obtain these two values, these two new values for ur and u theta. So this happens when the fluid is at rest at infinity, and the value of psi will of course adjust to this condition. The components of velocity with reference to a Cartesian coordinate system can now be obtained quite easily. For we can see that if we take u1 to be this value, u2 and u3, you can see this is taken such that u1, u2, u3 are velocity components in x1, x2, x3 conditions in the three coordinate directions. Then of course we have taken r square to be, if there is a vector r and it has a components in these three directions, then r square is given by this. This is a standard result that we know, and theta is equal to tangent inverse x1 square plus x2 square over x3 under root, and the angle phi is tangent inverse x2 over x1. Substitution of these values x1, x2 renders us u1, u2 and u3 from our equations of the solutions of the equations that are obtained for ur, u theta and so on. And having obtained these values, we need to find out the value of pressure also. The value of pressure turns out to be this equation, and where P infinity is the pressure, the value of the pressure at infinity. And therefore, taking together, we can write down the value of the Cartesian velocity component as u1 is equal to 3u over 4 into a times x3 into xi over r3 into a square minus r square minus 1 plus u into iota I into 3. I is a suffix, remember, running from 1 to 3, into delta into I313, where this delta is Kronecker delta Ij, and this, you know that it is equal to 0 if I is different from j, and it's equal to 1 if I is equal to j. So these are the results that we obtain for the solution for the flow past a rigid sphere.